This is lecture 30 of Physics 210A. Thermal physics, and today I am going to discuss with you very briefly a critical phenomena, focusing particularly on the liquid vapor phase transition, and also give you an idea that how this also corresponds to magnetic phase transition. So let me recall that when we were looking at liquid vapor transition, at that time on the PV diagram we had the PV curve as shown here. And as you approached this point called C, the curve became like this. And this C we called the critical point. And I had sent you a video showing CO2 liquid being heated up in constant volume. And there was another video also, or what you observe there, as you heat it up, keeping the volume constant. Earlier, when you had this, let me just symbolically make the container, and we had this liquid CO2 here. Slowly, it starts vaporizing, and it goes into a phase where the whole thing is homogeneous, and it becomes blurry. So what you are doing is, you are on the PV diagram you are increasing the pressure by raising the temperature, and you are going this way. At some volume, let's call it Vc. So this is isochoric heating of the gas. And it reaches this critical point. And when it goes above, this is supercritical. then there is no difference between liquid and vapor. So, by looking at this picture, you can learn a lot of things. So, let me keep making this picture. So, here volume, pressure, there is a difference between, let us say, V liquid and V vapor, and this difference keeps becoming smaller, and at this point this difference vanishes. There is also a specific heat involved. So, if you look at the curve, then at critical point you have, because these curves are drawn for constant T, T1, T2, T3, dP dV at constant T is equal to 0. And this implies that 1 over V partial P at constant T goes to infinity. So, at critical point, compressibility of the gas is very large, and that means even the gravitational field will make the density change quite a lot, or the volume change quite a lot. If you look at the corresponding TS diagram, it looks something like this. On the x-axis I have S, the y-axis I have T. There is this line of separation, and then you have graph like this. On this side I have liquid. You can guess because the entropy is very large. On this side, oh sorry, this is vapor. On the left side, I have liquid. And as you approach the critical point, the line becomes flat here too. So that at critical point, I have dt, ds at constant volume going to 0, which implies that T partial S partial T constant volume goes to infinity. So, CV becomes large. So, what it means is that as we approach the critical point, some properties start to diverge. And the example here that we saw was CV and compressibility. kappa. So, let us see what happens as you approach the critical point. So, again, if I take this curve, where I have V and P, this is the saturation curve. You have these graphs. What happens when temperature is increased? Keeping the volume the same, you go this way and you start reaching the critical point. You can also come from above. Now, as a liquid is heated, the specific volume increases, and that means its density starts decreasing. And at the same time, specific volume of gas starts, well, I should call it vapor, going down. This means its density increases. So, what you observe is that if I were to plot the density rho versus the temperature, you would have this curve for liquid and this curve for vapor, and the average density is kind of average of the two, and the density becomes the same as critical point. And this I will call rho C. Now, there is a principle of corresponding states that tells you something universal about the curve that we just plotted. If I were to plot the density divided by rho critical and T divided by T critical, the curves will look still the same, except that now I have scaled it and most of the gases fall around it. These are points for different gases. So, if I scale for each gas the density by its critical density and temperature by critical temperature, then you see this curve. So, they correspond to each other. If I were to then plot log rho over rho c with respect to Tc over T, this curve again looks like this, with most gases falling around it. So, this is the principle of corresponding states. Now, as we said earlier, with each critical point, there are divergences of properties associated. So, some property goes to infinity as you reach the critical point. Now, how do you measure these divergences? These divergences are measured, or what I'll call is related to something called the order parameter. This is something that tells you what's happening in the system. So, for example, when we looked at this curve for liquid vapor phase transition, on the left hand side I had liquid, on the right hand side I had vapor. The density of liquid and vapor is different, and rho liquid being greater than rho gas or rho vapor. So, I am going to call this rho liquid minus rho vapor to be my order parameter. And rho liquid minus rho vapor divided by rho critical. So, I have scaled it with critical density, is going to be called reduced order parameter. Now, you can see that if T is greater than Tc, there is no difference between liquid and vapor. So, order parameter is equal to 0, and for T less than Tc, rho liquid is greater than rho vapor. So, order parameter is greater than 0. So, order parameter changes across the critical point. So, what is observed is that, as I said earlier, Cv, as you heat the system up along the isochoric, goes to infinity as T approaches Tc. Compressibility goes to infinity as T goes to Tc. Let me call epsilon equals T minus Tc over Tc. So, it is observed that for epsilon tending to 0 minus, that means increasing temperature T to Tc. Cv at Vc goes as minus epsilon raised to minus alpha prime. And for epsilon tending to 0 plus, that means you are coming from above, it goes as epsilon raised to alpha. Similarly, compressibility. Kappa T goes as epsilon minus epsilon raised to minus gamma prime for epsilon tending to 0 minus, and goes as minus epsilon raised to gamma minus gamma for epsilon tending to 0 plus. The order parameter also changes as T approaches Tc. So, order parameter rho liquid minus rho vapor goes as minus epsilon raised to beta as epsilon tends to 0 minus, and above Tc rho liquid minus rho vapor anyways 0. Now, why should the should be minus beta? Why should the density fluctuate so much? See, the compressibility is very large, and therefore, even a small fluctuation in the pressure tends to change the density quite a lot. And therefore, what you observed in that experiment with CO2, that these density fluctuations make light reflect and the whole thing looks milky or shiny or blurry, because light cannot pass through. There's a lot of density fluctuations going on. Now, in the same manner as we did for gas, you can also see the magnetic systems. In magnetic systems, what you have is H, the magnetic moment, and TdS. So, in this case, you have du equals T ds plus H dm. This takes on the role of pressure, this takes on the role of volume, and the m is chi over T minus Tc times H, some constant, not chi, C. Chi is C over T minus Tc. So, again, across T equals Tc, there is a phase transition. You can already see that chi goes to infinity as T goes to Tc. So, other quantities other response functions also diverge as some power, it will be negative power of t minus Tc as the transition point is reached. So, near Curie temperature there is a divergence, that is also related to critical phenomena. So, with this I just gave you a small introduction to critical phenomena. Let me conclude my lecture. Critical phenomena has been introduced. The idea is that near the critical point, a system has large fluctuations and certain quantities diverge. Thank you.